Hello everyone, welcome back to my channel. Today we're going to go over this problem of fluid mechanics that deals with control volumes and control surfaces and conservation of mass. So in the midst of a steady rain shower, the weather report states that 2 inches of rain have fallen in your area in the past hour. Consider a conical vessel of radius 1 inch at a height of 4 inch. Derive an expression for the height of the rainwater in the vessel as a function of time. How long does it take to fill the vessel in hours? So we first look at equations that we might need. So we need the conservation of mass equation for sure, which is given by this um, ddt of control volume and control surface, where this is a relative velocity. However, in the case of a fixed control volume, that is equal to v. And let's see what each of these terms mean in more detail. So this equation comes from the continuity equation, specifically the integral form of the conservation of mass in fluid mechanics. So let's break down where it comes from. So the starting point is the conservation of mass, and this principle states that mass cannot be created or destroyed within a control volume, CV. So the rate of mass accumulation within the control volume plus the net mass outflow through the control surface is equal to zero. So expressing it mathematically for a control volume with a control surface CS, we have ddt of control volume rho times dv plus uh, integral over the control surface of rho times relative velocity times dA is equal to zero. So rho is the fluid density, v relative is the velocity of the fluid relative to the moving control surface, dA is the outward normal area vector on the control surface, and integral of control volume of rho dv is the total mass inside the control volume, and d dt is the time rate of change. This version accounts for a moving or deforming control volume. For a fixed control volume, if the control volume is stationary, the relative velocity equals the absolute velocity. So relative velocity equals v. Then the equation simplifies to this equation. This is the integral form of the continuity equation for a fixed control volume. Relation to a differential form. Applying the divergence theorem and moving derivatives inside the integral gives the differential local form. This is the familiar continuity equation in differential form. So here's the summary. Um, so let's go back to a problem. So for this problem, we first have to pick our control volume. Um, yes. So we'll pick our control volume to be something in which mass is conserved, basically. Um, yes. And wait, hold on. Yeah, so basically, I'm gonna choose the control volume to be this surface over here, since as we see, the mass accumulates in this region and the mass flows in through this region. So the mass flowing in through this control surface must equal the mass that accumulates in this volume. So we will perform mass conservation on this control volume. So basically we have the velocity of the rain, we have the radius of the cone, and we also have height of the water. And the larger height, which is 4 inches. So our first thing first is to always write the governing equations, which is the conservation of mass equations. So d dt of control volume times rho dv plus integral of cs rho u relative dot delta a is equal to 0. So we have to find what each of these integrals are. As you see over here, for the control surface, we have this top, and the rain is falling through that top, that area of the top. And the U rain is the U relative, and the rho is the density of water. Over here, on the left in the control volume, we have rho times dV, and it's basically representing the water accumulating inside. So this states that the water accumulating inside plus the kind of the rain flowing into the control volume is equal to 0. So essentially, um, this value is going to be uh, rho, the density of water, multiplied by this volume of water that is accumulating here. And this volume is the volume of a cone of height h, as we see over here. Um, yes. So it's equal to rho times the volume of a cone, which is 1/3 pi r cubed. Except over here it's going to be, no, 1/3 pi r squared times h. So times 1/3 pi r squared times h. And we're going to differentiate this with respect to t. And what about this control surface over here? Well, the rain is falling through a circle of radius 1 inch. So dA is going to be that circle. We're going to have rho times U relative, which is U rain, uh, and multiplied by dA, which is the area of that circle, which is pi r squared in general form. Um, yes. And so basically, this one is going to be negative as well, since the rain is falling through the control surface, and the vectors of U rain and the vector of the control surface pointing upwards are opposite each other. And dot product, basically dot product, what it is, when you dot two vectors, you're saying UV cosine theta. And cosine theta over here is 180 degrees. So cosine of 180 is -1, so we'll get negative UV in magnitude. So that's where the negative sign comes from, because these two vectors are pointing opposite to each other. As the U-ring falls down, and this is the normal vector to the surface of the control surface, which is pointing in the opposite direction as U-ring. Yes, so now we know that much. And it can be kind of confusing because these radius are actually different from each other. So don't get it confused, but I'm just writing it in general format now. So for the first one, we have d dt of rho times 1/3 pi r squared h. And whenever we have an equation like this, it is always good to get it in terms of lesser variables. And we note that we can get a relation for r in terms of h by using similar triangles. We can call the 1-inch radius r, and uh and we know the height, which is 4 inches. So we can call it h. So basically, r over h is going to give us a slope. So r over h is directly proportional to um this radius, which is r, over small h. As you can see, it's similar triangles. So we have big triangle over here and little triangle over here. And then we can solve for r is equal to RH over big H. Um, yes. And then we can in turn plug it in into this equation to get d over dt of rho times 1 over 3 pi r squared over h squared times h squared times h, which is h cubed. Now we have constants. So rho 1/3 pi and r squared over h squared are all constants. So when we differentiate this, it becomes easier. And we are left with rho pi r squared over 3h squared times 3h squared dh dt. And the threes cancel out actually. So we are actually left with um rho times pi times r squared over h squared times h squared times dh dt. Now for the second part of the control surface, we already found the value. And basically this why the unit analysis makes sense is because why both of these will give you mass is because we have rho, which is density. Density is in units of mass over volume. And we have volume over here. So mass over volume times volume will give us mass. Over here, it might be less apparent, but velocity is in meters per second. Rho is in meters, uh, or wait, hold on. kg per meter cubed. And dA is in units of meters squared because it's an area. So we have area times velocity times density. So m squared times m will give you m to the power of 3. And then the m to the power of 3 cancel out on both sides. So it will give you a kilogram over second. And actually, this is why you might ask yourself, well, this unit is kilogram over second, but this unit over here is just kilograms because it's a mass. So where does the kilogram over second comes? Well, that's why we differentiate it with respect to time to get it in terms of units kilogram per second. Basically, it states that the rate of mass accumulating in this control volume is equal to the mass entering the control volume through the control surface. Yes. So, yes. So we now combine these two quantities. So rho times pi times r squared over h squared times h squared dh dt minus rho times u reign of pi r squared is equal to 0. Um, and certain terms cancel out like the rho and also the pi. So we are actually left with r squared over h squared times h squared dh dt is equal to u reign times r squared. And we can now integrate both sides actually with respect to t. So integral of r squared over h squared times h squared dh. Oh wait, sorry. First, we actually use separation of variables. And we rewrite it in the form r squared over h squared times h squared dh. And we multiply both sides by dt, so we get u rain times r squared times dt. Now we can integrate both sides. So we integrate the first side, r squared over h squared times h squared dh from h is equal to 0 to 0 to h, which is, I believe, yes, 0 to h, because we want to derive an expression for the height of the rainwater in the vessel as a function of time. So from 0 to h. And this is equal to integral from 0 to t of u rain r squared dt. And yes, and basically we have r squared over h squared times h3 over 3 evaluated from 0 to h. And it's equal to u rain um we have a problem here actually. Oh wait, sorry. We didn't substitute r is equal to rh over h for r squared on the left. So we actually should do that before we go through this whole integration. Yeah. So, okay, r squared over h squared times h squared dh over dt is equal to u rain times r squared over h squared times h squared. So actually, all these terms cancel out. Well, is it true? Wait, I'm confused. Oh, I understand where the confusion comes from. So remember the time when I said that I was going to get confused by this R over here since it's a different R value? So I forgot to change it to capital R because that is actually what it is, since it comes from the area of the control surface, which is pi times R, which we define to be 1 inch squared. So just be careful of that. So this is actually R squared. And yes, the same things apply, except the R squared also cancels out, I believe. Yeah, the R squared cancels out. So we are left with h squared over h squared dh is equal to u rain dt. I believe. Yes. And then now we can integrate. So we integrate from 0 to h of h squared dh and is equal to integral from 0 to t of h squared u rain dt. So we have h cubed over 3 evaluated from 0 to h is equal to h squared times u rain t from 0 to t. So it's equal to h3 over 3 and it's equal to h squared u rain T. Yes. And thus we can find an expression for h as equal to 3 times h squared times u rain times t to the power of 1/3. Yes. And that matches the answer that we were expecting at the beginning. And how long does it take the vessel how long does it take to fill the vessel in hours? This part is easy because we have already done the hard part. So let's go ahead and do it. So basically the height of the vessel when it fills is going to be 4 inches. So for B we said 4 is equal to 3 times the height, which is 4 inches squared times U rain, which is, yes. So U rain is actually, it says that 2 inches of rain have fallen in the past hour. So U rain is going to be equal to 2 inches per 1 hour times 1 hour over 60 minutes. Or actually, we don't have to convert it because their final unit is in hours. And over the time, which is what we are solving for. We set it to 1/3. So basically, we evaluate this when h is equal to 4 inches because the height of the vessel is 4 inches. And if we solve it, what do we get? Mm, we get t equals 2/3 hours. And we did it by cubing both sides to get rid of this exponent here, and then solving it just like simple algebra. Thank you guys so much for watching this video. Here's a quick recap of the whole problem. I'm going to be posting the slides as usual in the discussion, and don't hesitate with questions. See you next time.